Good morning or good afternoon, depending on where you're at. And welcome to today's session on 3D printing composite parts as strong as aluminum. My name is Kanan Irons. I'm a 3D printing application engineer at Hawk Ridge Systems, and I'm going to be showing you how to do just that, to print composite parts as strong as aluminum. A few housekeeping items before we get started. If you'll take a look at the right side of the screen, you should notice there's an area for chat and an area for questions. We have moderators on standby from our 3D printing team that are willing and eager to interact with you and respond to questions. So feel free to use those tools throughout the course of the presentation. And a little bit about my background before we get started. I started out as a mechanical engineer, and my first job, I was stationed at a machine shop in West Texas. And we primarily supported the wind energy sector, wind turbines. And at that machine shop, we produced all sorts of aluminum and steel components. We used CNC equipment, mills and lathes. We even had a water jet. And so when I heard about a printing system that can produce parts that are on par with that type of strength, that aluminum-like strength, I became very excited, because there's so many benefits to moving to a printing platform as opposed to a traditional method. And so I'm excited to share that with you guys this morning. And with that, let's go ahead and get started and take a look at the overview of today's session. We're going to start out by looking at what type of printer can actually achieve this aluminum-like strength. And then we're going to look at the technology behind that, which is called continuous filament fabrication, or CFF. We're going to follow that up by looking at the data, the mechanical specs, because we need to prove this bold claim that we've started this webinar off with. We're going to look at how the actual sample was tested to produce that data. And we're going to look at the different types of fiber that are out there and what strength properties and what use cases each one of those have. And then we need to bring what we've learned from that mechanical data and bring that into your own part designs. And so I'm going to give you some tips on optimizing designs for maximum part strength. And then we're going to follow it up with a live software demonstration to look at the workflow and what it takes to prep a print before you produce it. And then we'll cap it off with some real world applications and show how these parts are actually being used out in the field. And so we got an exciting list of content for you today, and let's go ahead and start with what type of printer can achieve aluminum-like strength. So the printing system is going to be a Markforged printing system, and Markforged has paved the way in producing these incredibly strong composite parts. And they've done that through the use of two technologies. The first one, you'd probably be very familiar with it, called fused filament fabrication. Another term used for it is FDM. And that's the act of extruding material out of a nozzle and building a part up layer by layer. But Markforged has combined that technology with CFF, or continuous filament fabrication. And that's the act of ironing in continuous fibers into a plastic matrix. And when you're able to combine those two material categories, you get the best of both worlds. And the fibers produce those very strong parts. If you take a look at the left side of your screen, you'll see the plastics. You have onyx, nylon white, and a flame retardant onyx. So onyx in itself is very strong. It's a nylon base mixed with chopped carbon fiber. And it's stronger than many common printing materials on the market. But the true strength, the strength that I'm talking about with aluminum, it comes from reinforcing these onyx, nylon parts with the continuous fiber, and specifically carbon fiber being the strongest of the fibers listed there. And going back to that machine shop idea, how an aluminum part is traditionally manufactured, you think about all that's involved there. You think about the facility requirements for a machine. You think about the special power requirements. You think about compressed air and the amount of skill that it takes to run a traditional CNC machine. Then compare that to a printing system. So what you see pictured here is a picture of the X7 industrial system from Markforged. And they also have a desktop model that's about half the build volume. But these systems are office friendly. You can plug it into a 110 outlet, and they're quiet, and they're easy to learn how to use. And so right away, you could see some major benefits from moving to a printing system as opposed to a traditional method. And just to think, you're able to produce these strong parts right there next to you while you're designing the next revision. And take a look at the footprint of this machine, about 23 inches by 19 by 36 inches tall. That's much smaller than a CNC machine, and that could fit right next to you, next to your desk while you're working. And it still has a great build volume, 13 inches by 10.6 by 7.9. And so you're able to produce these larger parts in an office-friendly environment. And so that's very exciting, especially as an engineer, as you're going through multiple design revisions, you're looking at quick turnaround times. And so that's some key advantages right off the bat. Now let's take a look at the continuous filament fabrication and process in more detail, just to show you a little bit more about how it works. If you take a look at the video on the right-hand side of the screen, you'll see the printing system ironing in these Kevlar fibers into an onyx part. Take a look at those yellowish fiber strands on the perimeter of the part and around any internal holes. And also look at the infill structure. So it's a mostly hollow core that's reinforced by these continuous fibers. And now the fiber routing can be customized and optimized depending on your loading conditions. And the machine's able to complete this by the use of two different extruders and two different nozzles. You have on the left side of the screen, you can see there's a fiber nozzle and a plastic nozzle. And so changing material is easy as changing the spool. So with each part, you just need to select what fiber you want and what plastic. And there are cases, let's say you're producing an enclosure with low loading conditions, you could just choose to print plastic only. And so you have that flexibility. Now let's take a look at the different types of fiber in more detail, because each one of them has unique applications and unique properties. You see the list of 4 fibers here, starting out with the carbon fiber. That's the strongest material that Markforged offers. It has the highest tensile strength. We see this used in all sorts of applications, from brackets to lifting fixtures. Really, the sky's the limit. Anytime you need these really strong, stiff, and rigid parts, carbon fiber is a great choice. Then we have the HSHT material, which is also a type of fiberglass. That means high strength, high temp. And the HSHT is very strong in itself, but it has the added benefit of retaining that strength under elevated temperatures. And so it has a high heat deflection temperature of 150 degrees Celsius. We're seeing these used in any applications that undergo elevated temperatures, such as molds or parts that need to undergo higher temp processes like autoclaves. And then we have the Kevlar. And where you think about where Kevlar is used in other parts of the world, you think about bulletproof vests, those times when you need that high impact resistance. And Kevlar is excellent under repeated loading, and it has more elongation before break, and so it's able to absorb more energy. We're seeing this used in situations like end effectors, these gripper jaws on robots that need that repeated loading over and over again. And then last, we have fiberglass. And fiberglass will strengthen your part significantly over an unreinforced part, yet it does it in a more cost-effective way. And so it gives you that cost-effective strength. And you can see at the bottom there the pricing per cubic centimeter, and it is very affordable to reinforce parts with fiberglass. And there are applications where you don't need that extreme strength that you get from carbon fiber. And so it's great to have that flexibility to switch between fibers as you print different parts. Now let's take a look at the fiber layout patterns here. And you'll see on the top row, we have what is known as a concentric fill. And I like to think of this as racetracks going around and around the part. And there is some customization with the concentric fill pattern. You can choose to do all the walls like that video that we saw earlier, or you could choose to do only the outer shell or the inner holes only. you also have the ability to increase the number of strands in that concentric pattern. And you could completely fill the interior perimeter of the part for that layer if you wanted to. But then we have there at the bottom isotropic fill. And notice how those fiber strands are laid out in a specific angle, about 45 degrees. And so with isotropic fill, you're able to really dial in the direction of those fibers in order to maximize the performance of that part under a given loading condition. And you could even choose to alternate the angle of those fiber panels as you move up in the z-axis as you're printing. And what that does is provides multi-directional part strength. And so just think of the example of maybe a dog bone where you know what direction the load's going to be. Let's say it's a tensile test. And so you're able to orient those fiber strands in the direction of that load and really maximize your performance. But there are many cases when you know the part's going to experience all sorts of loads in multiple directions. And that's when it's great to utilize that ability to change angles between fiber panels. And there's a theory that goes behind this reinforcement of parts, and that theory is called sandwich panel theory. You see the little picture on the left side of the screen of a composite sandwich panel. That's the idea of having a mostly hollow core, or a honeycomb matrix, capped off by strong panels on the top and the bottom. So that same principle goes into efficiently strengthening your parts with these Markforged systems. And you see in other parts of the world, think about the I-beam design, where you have more material on the outside of the part in order to improve the bending strength and efficiently put strength where you need it. And if you take a look at the top right hand of the screen, we see a beam that's supported on each end with the load in the middle. And we think about the forces going on inside that beam, and the highest forces are on the top and the bottom of the beam. You're going to have the highest compressive force on the top and the highest tensile force on the bottom. But when you look at the neutral axis there, the load is minimal. And so that's part of the theory that goes into reinforcing these parts, and you see the picture on the bottom right. When you're able to place fibers in these high load areas, specifically areas in tension, because that's where the fibers are strongest, is in tension. That's when you're able to get these really strong parts, and you're able to do that in an effective and efficient manner. Now let's take a look at some of the data, because we need to back up this claim of parts that are strong as aluminum, and I'm going to show you that it can be even stronger than aluminum in certain cases. Take a look here at the two charts. We have a flexural stress and strain curve for plastics and for continuous fibers. And remember, flexural strength deals with the bending strength. How strong is the part when it's under a bending load? And starting out with the plastics there on the left-hand side, we have onyx, which again, it's a very strong printed material, mainly due to the inclusion of that chopped carbon fiber. And it's stronger than another common printing material that you're going to see out there called ABS. But again, that real strength comes from reinforcing an onyx part with the continuous fiber. And you see onyx on the right-hand side of the screen. It's at the bottom of this chart when we're looking at parts reinforced with fibers. And the carbon fiber actually outperforms 6061 aluminum in a flexural test. And notice the behavior is very similar in the linear region of the curve here, yet carbon fiber is able to reach those higher flexural stress values before breakage. It's also important to note how each one of these fibers performs under a flexural load. Take a look at Kevlar, for instance. We see that there's quite a bit of strain before the part actually breaks. And so it's able to absorb a large amount of energy. And then we have the high strength, high temp fiberglass, which it in itself almost reaches the maximum strength of aluminum. And then we have aluminum there. Aluminum, again, it has a linear curve for a while, then it tapers off after that yield point. And that's where carbon fiber starts to outperform the aluminum. But also look at how much the aluminum will stretch before breakage. And so that carbon fiber, it has very little movement before breakage. And so you're going to be able to withstand a really high load and then all of a sudden the part will snap under the maximum loading condition. And I'm going to show you a video of a tensile test that shows that in more detail shortly. But let's look a little bit more detail at the numbers here. And I want you to let's focus on the carbon fiber for a second here. So if we're looking at tensile strength and flexural strength, when you compare that to an onyx only part, you see on the far right hand side of the screen, it's several times stronger than an unreinforced onyx part. It's really incredible the amount of strength benefit you can get from reinforcing parts this way. And by the way, we're going to go ahead and drop this mechanical data sheet in the chat so you guys can take a look in more detail. And it's going to have a few more items that may be of interest to, especially to the engineers out there. And now let's take a look at how the test specimen was made and how it was tested. And we're going to look at the test specimen for the flexural test. And so this specimen underwent a 3-point bending test, where you have a beam supported on each end with a load in the middle. And the actual sample was produced on a Markforged machine, and it's about 4.5 inches long, almost half an inch wide by about 1/8 of an inch tall. But it's important to note the fiber directions in this part. Notice how they go along the length of the part. And again, that's so that all the fibers are placed in tension, especially on the bottom there. The fibers on the bottom are placed in tension under that load that would be in the middle. And so these fibers are unidirectional, and it was completely filled with fiber, and it had full infill. So it is really optimized to do well in this test. And that's why it was able to outperform aluminum, because we used the best strength properties of the carbon fiber in order to maximize the performance. And so now I want to give you a few tips on how to bring some of these techniques into your own part designs, because at the end of the day, that's what we're looking to do. And so the first tip I'm going to give you is to route your fibers according to loading conditions. And again, it's placing those fibers so that they're loaded in tension under your expected loading conditions. We have the picture of the dog bone sample here. It's under a tensile test, and all the fibers are oriented in the direction of the load. On the right side of the screen, we see an isotropic part that has several isotropic panels that are rotated at specific degrees. And in this case, we have a part with 3 fingers. And notice how every third panel, the fibers are laid out in the direction of one of the fingers. And with the software that comes with Markforged systems, you're able to do that, to actually route the fibers so that every third one, whatever it is, let's say you had 4 fingers, you're able to do the same thing by changing the angles. And what that does is it's going to make it much stronger in multiple directions. And notice how we have each panel there alternating angles as it goes up. And so that's the first tip, to place fibers so that they're in tension. The next one I want to tell you about has to deal with print orientation. And this is very similar for other systems that use the fused filament process. And this tip is to orient your structural members in the X and the Y planes. And now this is very important for fiber reinforcement, because the fiber is actually laid out in the X and the Y plane. And so the key here is to maximize the amount of cross section in that plane, in the X and the Y planes, so that you could fit more fiber in. And the parts by themselves are much stronger in the X and the Y plane compared to Z. You could see easily from that example of the flexural test specimen. On the left side, we have it printed flat, and on the right side, we have it printed facing in the Z axis. You have much more strength in the X and the Y planes. And so optimize your part designs so that this is true when you print. That's the second tip. And now the third tip, it's a little more involved, but you're going to get the benefits of having complex geometries and having that part strength in multiple axes. And that's to split up parts to create optimum fiber routing. You'll see on the left side, we have the example of a right angle plate. And going back to that tip of X and Y, maximizing the amount of area in the X and the Y plane, it's easy to see that the vertical member on that right angle plate isn't going to get the most benefit out of fiber reinforcement. And so when we're able to actually split that part, route the fibers optimally, and then put it back together, we do get the benefits of both worlds, that complex geometry, at the same time able to retain that strength that can come from Markforged systems. And you see the example of the sketch on the right that's showing the same thing. The shaded areas would be facing down on the print bed. And so when you're able to split the part and print it that way, you're able to fit much more fiber in. And in that part, you see the large holes there going through the middle. You're able to effectively reinforce those holes. And so that's the third tip, to print each section so that fiber can be routed optimally. So now let's take a look at the Eiger software. So Eiger is the slicing software that's used to produce these parts. And we're going to have the guys in the chat drop a link to this software so you can try it out for free. It's actually free to use, and we highly recommend it. So sign up for an account, drop some of your designs in, and take a look at the workflow for yourselves. And I'm going to give you a short overview now, but it's always good to understand what parts would cost that are routed with fiber, what's the print time going to look like. And that's a great way to look at how you traditionally manufacture these types of parts and compare. And you'll see the savings, the time savings when you think about lead time, and then also the convenience in being able to print, use a printing system. And so we're going to take a look now at the Eiger software, and we're going to go through the basic workflow of prepping a part for print. I'm going to switch screens here. And so now this is an overview of the Eiger dashboard. So notice how we have multiple part designs. We have a folder structure. And us at Harkridge, we love to separate folders based on customers, projects, and users. And this platform really allows multiple users to collaborate together. And so other engineers can come in and look at parts and help me edit them, and we could collaborate together. So it's a really great platform. And it also allows you to remotely send jobs to any printer. For instance, I'm here on the West Coast. I'm able to send prints to the East Coast. And someone in the office there on the East Coast could simply press start, and it's good to go. And this has been very useful, especially this year with all the COVID restrictions, being able to remotely send these print jobs and remotely prep them. And so it's a very versatile software. And it also allows you to monitor each system. And so, for instance, we could take a look at our devices and understand the status of any one of those devices. And so you can see we have several X7s, we have some of the desktop and even metal systems. And so we're able to monitor those and understand if there's anything in the queue, what's next in line. And so it's really great for being able to keep track of things. Another quick organizational point here, the software actually allows you to keep track of your material usage across different users and devices. And so this is really great at the end of the month when you're trying to understand how much has been printed, how much am I spending on material, and you could even look at parts uploaded per week. You know, I could take a look at my parts uploaded in the past few weeks, and you could get a curve and understand what's being done and how much material is being used. And so it's a very useful tool. And you can see our organization, we have 20 users and 16 devices and over 2,000 parts. So we're staying busy with these machines. So now let's take a look back at the actual workflow here. And so to start out with, you're going to need an STL file. So if you have a CAD software like SolidWorks, it's simple as exporting as an STL file, and then you'll drag it into Eiger. And that can be done here. You just drag and drop, and you're able to rename the part and create a folder for that part or project. And once you've done that, then you come into the build platform. And so we have that part that I showed in the slide earlier about splitting parts for maximizing strength. And I just want to go through a few concepts with this part design, and we'll be able to see up close why it's important to be able to route fibers optimally. But a few key things right off the bat. You can see I have a virtual build platform, and this is the build platform of the X7 system. I'm able to scroll through the different machines that Markforged offers and even the metal systems. And so that could be great. Sometimes you want to compare what a metal printed part would compare with a carbon fiber part, for instance. And so it's great to be able to have that flexibility. We're also able to select materials, onyx being the most common for Markforged. But again, we can go through these and look at what the part cost would be with different materials. And then also the fibers. So let's do the example of an onyx part reinforced with carbon fiber. And first off, when you bring your part into the build scene, the first thing to think about is print orientation. And it's easy to change the print orientation. It's as simple as clicking on a flat surface. And something to note about these types of systems, these fused filament systems, support is generated on any overhangs, for the Markforged one specifically, any overhangs over 40 degrees. And so if we had a 90-degree overhang like this, we'd expect support to be generated as that part's built up. And so again, it's important to maximize that XY cross-section, and so that you're able to, one, fit more fibers in, and then also it helps minimize the amount of support that's generated. And in this specific part, we would expect support to be generated maybe in this midsection here. The other settings that we can play with include the layer height. And so the industrial systems can go down as far as 50 microns in the Z-axis. And we do see differences, let's say 50 compared to 100 microns. The main place you see differences is on curved surfaces. Think about a dome shape on top. You really see a smoother surface when you're able to get that finer resolution. And so that's great to have that ability. And now parts that are reinforced with fiber are constrained to the diameter of the fiber itself. And so the carbon fiber, it has a larger diameter, it's going to be at 125 microns, which is still very good. And you can also see we're able to change the support structures, adjust the support angle. Think about the case of maybe an arm that's overhanging in a certain direction. You're able to actually angle that support so that it can be perpendicular to that arm, for instance. And then we have other features such as brims and changing the speed of infill. And then the next thing that we can do is take a look at the infill structure itself. And in that video I showed at the beginning, we saw triangular infill structure. And triangular gives you the best of both worlds. It really provides a strong part, yet you're efficiently using your material. And a lot of the strength is in the walls of the part anyways, talking about those extreme sides of the part. And so with this system, you're able to change that pattern. So a hexagonal fill has a great strength to weight ratio. And then your rectangular and solid infill structures are going to be more dense. And remember that flexural test specimen, it had a solid fill. And we'll use this typically for smaller parts. It's good to use solid infill. But as you get to larger parts, you're really getting the most benefit out of doing a triangular fill. One, because it's going to really speed up your print time. It's going to save you on material. And then you're also able to adjust the density of this pattern. And Markforged is really good about suggesting default settings that work really well. And so it's very rare that we do edit these, but there are certain cases once you really get into it where you might want to maybe make the part more dense or add any more roofs or floors or walls. And so you have that ability if you want to do that. But again, most of the general settings are good to go. And so once we have all of our settings complete, we're then able to understand, one, the part cost and also the print time. So these are very important factors, especially if you're looking at justifying a system like this. What's this part taking to produce, and how long was the lead time before? Let's say if we're in a CNC environment, I know in our shop, we would have to order bar stock. So as soon as I got the engineering drawing done, we have to go and order that type of stock of material. And that would take a few days. And we'd also have to order tools in order to produce that part, whether it's a special end mill or anything to do chamfers or radiuses, any types of cutters. And so you start to compare that to what it traditionally takes to produce a part. And then you also look at the cost. And so again, a great thing about a printing system is you can have this running overnight, unsupervised. And so you start it at the end of the day, you come back in the morning and you have a fresh part. And that really speeds up the process as a designer. As I'm sure many of you know, you're able to turn around those revisions quicker and find the right solution much faster that way. And now let's take a look at the fiber routing. This is the really exciting part about the software. And so what we're able to do is look at the internal view of the part. We're able to go layer by layer and understand how the part is printing. And so this part, we have a couple of different colors here. One of them is this purple area, and that's your support structure. And remember, that's generated on any overhangs over 40 degrees. And we can see that's supporting the part as it's being printed. But we also have these blue areas, and that's the fiber that's being laid out. And so let's take a look at the 2D view to see the fibers in more detail. And so here's the base of the part. That's going to be your onyx material, and that's one of those floor layers. And as we build up, Eiger automatically will lay out fiber on the bottom and the top of the part. And that goes back to that sandwich panel theory that we looked at earlier, where you're getting the most strength at the extremities of the part. And take a look at how the fiber is naturally oriented. And so it looks like we have about 6 layers here, and we have an isotropic fill pattern. And the angle of the strands in this case is at 45 degrees. But as you work your way up, you see how that angle changes. And again, you could customize each individual panel based on layer and the type, whether it's isotropic or concentric. Now, going back to why it's important to alternate these angles in certain cases, think about this angle here. So we're at 90 degrees, the fibers are facing vertically. What if we were to reinforce this part completely with these 90-degree panels? Think about loading conditions. And so if we bent the part along a vertical axis, those fibers wouldn't be placed in tension. And so you wouldn't be getting the most out of the system. And so that's why it's important in many cases to alternate. And so this particular panel isn't very strong along the vertical axis, but take a look at the next one. It's angled 45 degrees, and then so on. This one's actually horizontal. And so the ability to stack these panels together provides that multi-directional part strength. Now let's take a look at the vertical member, because remember we talked about splitting up parts to optimally orient fibers. And let's take a look at the automatically generated one that's here on the top of this part. So I'm going to scroll all the way to the top. And one of the layers, it looks like we have about 4 strands. And think about what loading conditions would put these fibers under tension. You can see maybe if it was bent around the Z-axis, so you could have some additional part strength. But what about if the part was bent along a horizontal axis? You wouldn't be getting the benefit of that fiber reinforcement. And so that's one reason it would be important to split this part if you really needed that part strength. Now let's look at how we might edit some of the layers. And editing layers is as simple as selecting groups of layers and then saying that you want fiber in them. And so a good strategy here is to find any surfaces that are flat and large cross-section. And so in this case, let's edit about 6 layers or so. There we go. We got about 6. There we go, 6 layers. And that's towards the top of that base portion. And so what we're going to do is create a group, and then we're going to use fiber in that group. And so as that's generating, you're able to select different areas of that part and individually customize the fiber pattern in that area. And so going back to the overall part here, let's take a look at this fiber configuration. So here we go, very similar panel to the bottom now. And so we created that sandwich panel that we talked about earlier. But what if we wanted to adjust this and change it from isotropic? We could do that by just simply clicking concentric. And when we go to a concentric pattern, remember we're talking about those racetracks, those fiber strands that go around the perimeter. And in this case, we have all walls selected. And that means the outside and any inner holes. But we could also increase the amount of concentric fiber rings in this particular part. So let's go ahead and do that. Let's increase it a few fiber strands here, or rings. And there you go. And so in this case, you can see we have quite a few more racetracks that are going around the part. And there are loading conditions where this is actually a great reinforcement strategy. I'm actually going to show you one of the parts that this is the case. It's called a double link. It's a chain link. And so parts that are shaped that way, like a chain link or a racetrack, tend to benefit more from this type of fiber layout pattern. And so I was able to edit just that one layer, and I could select multiple layers and even add fiber in other parts of the geometry. And so you have that, again, that flexibility to add fiber where you need it. And so the next thing I want to take a look at is how this part would perform if you split it up. And so what I've done is taken that split part design, and here we have that vertical member, and now we're able to orient it in the X and the Y plane. And when we're able to do that, it will significantly improve the amount of fiber that can be placed in the part. So let's take a look at the internal view here. So now on that internal view, the default Eiger suggestion for fiber is actually really good for this one. You can see it automatically generated that sandwich panel. And now we have that great strength, that great bending strength in all directions. You can see each panel, again, angles as you go up. Then we get to the mostly hollow core of the part. Notice that triangular infill structure. Notice the amount of wall strands. And then as we work our way to the top of the part, then we have more fibers being laid out. And so it's easy to see that this panel is going to be much stronger now. And then let's go ahead and take a look at the base while we're at it. So here's what that split base would look like. And so we have a slot for the vertical member, and then we have some bolt holes. And putting threads in printed parts, there's a few different strategies for that. And one strategy that we like to go through is to use heat set brass inserts. And so that's as easy as adding a soldering iron and a brass insert and just pressing that into a hole that's slightly smaller than the brass insert itself. So that's one strategy. And then also you are able to print threads in certain cases. And the balance really is going to depend on how much you expect to assemble and disassemble the part. And so if you expect to put the part together and not disassemble it very much, you can look at printing your threads. Let's take a look at the internal view of this one. So I went ahead and added some more sandwich panels to this part. And we looked at those areas of high XY cross-section. And moving up, very similar to the original part that we looked at. We have that mostly hollow core again. And then we have the sandwich panel to cap it off. But then we have this other section of rectangular geometry that we also reinforce. And so the way this system works is once the onyx layer has reached an area where there's fiber, then the fiber extruder kicks into gear and starts to iron in those fibers into that layer. And so that makes it a very efficient process as the part is being built up. And in the end result, you're just going to see what looks like an onyx part, but inside it has these continuous fibers. So with that, let's go ahead and go back to the presentation now. And I want to tell you the story about this part called the double length. And here's a little snapshot of it there. It's a chain link. It kind of looks like a racetrack. And there's a really neat story about this part, especially when it comes to part strength. So I'm going to go back to the presentation now. And so This double length was developed by Markforged, and the goal with this part was to lift a 10-ton truck. And so we're talking about an onyx part reinforced to the max with carbon fiber. And I want to show you the tensile test. So they actually tested this part for maximum strength, and the results are amazing, really. And we'll see. So 20,000 pounds, 10 tons. Let's take a look at the tensile test. So here we have the part that's constrained on the bottom. The part's being stretched on top. And look at that, we're over 21,000 pounds now, about to reach 22. It's getting pretty close. And there it goes. I don't know if you could hear in the background, but people were yelling when that happened. It's pretty exciting too, because think about that. It was around 22,000 pounds of force on a printed part, and this part fits in the desktop model. So think about that, a part that's that strong, that's being printed on a desktop. And also notice how it broke. So going back to that mechanical flexural stress and strain chart, remember we saw that carbon fiber, it reaches its maximum strength and there's not much stretch before breakage, and that's exactly what we saw here. And you can see some of those fibers that end up protruding through the part. You can see some of those fiber strands as they were ripped apart. But again, this part was loaded so that those fibers are in tension. And so they were really able to optimize this part for the tests and its application, which is to lift things. And so there is a company that took this part design and they've used it in their manufacturing line. And I want to show you a little video on that now. And so the company is called Kloss, and they produce farming equipment such as harvesters. And these systems are very heavy. And we'll see it's a little over 17 tons for one of these. And they've been able to utilize that double link part to lift these harvesters into the air and move them around the facility. And so a machine over 17 tons. And going back to that Markforged part, it held a little over 10 tons, about 11 tons. So what they have here, take a look, they're connecting a Markforged part, and that one's actually out of nylon white, but it's fiber reinforced. And they have 4 of them. And so you can see you would need 2 of them if it was just the carbon fiber, but they had 4 lifting points, so that's what they did. And take a look at that. Man. Completely supported by parts printed on a desktop system. And that allows for quick connections so they can easily move equipment where it needs to go. And I just think that's incredible that you could produce that type of strength off of a printing system. And now let's take a look at a few more use cases. And most of these are going to have fiber, but some of them don't. But I just want to show you guys how these parts are being used out in the field. And the first category here, so let me jump back for a second here. I wanted to include this as well. This is a stress strain chart of that same double length. And so I took SolidWorks and I did a finite element analysis, and I looked at what would it take to yield an aluminum version. And it turns out that at about half the strength, so we're talking about 10,000 pounds or so, that the aluminum part would begin to yield. And so if you're not familiar with stress strain charts, the areas that are red have the highest stress, and the yield strength here is shown on the graph. And so any areas that are above this bluish color, that's where the part's starting to yield. That's when things are starting to move and they don't return to their original shape. And so it turns out this part was beginning to yield at half the strength, half the load of that carbon fiber reinforced part that we saw earlier. And so again, this is proving that Markforged parts can be much stronger than aluminum in these optimum fiber routing conditions. The other thing I wanted to show you before we jump into more applications is a cost analysis of the double link compared to CNC, compared to a printed version. And so I went out and got a quote on a 2-day turnaround, because that's what you're getting with the printing system. You're getting a very quick turnaround. And on a 2-day turnaround, we have a part that's about $600. And when you compare that to the reinforced onyx carbon fiber part, that's around $500. But we saw that in that example of the harvester that they used 4 of these parts, and so the loading requirements on each individual length wasn't quite as high as this one with the onyx and carbon fiber. And so you could even bring that down to an onyx with fiberglass if you had 4 of them. And you're at half the cost of what it would have taken to produce that in a CNC method. And so it's this type of analysis that's really good to do when you're looking at the parts that you're making now, the time and labor involved in producing those parts. And then when you think about placing this on a printing system that can print unsupervised in an office, you really start to see some of these major benefits to going an additive route. And so with that, let's take a look now at some of these applications that are out there. The first one I want to mention is fixtures. So we're seeing Markforged parts being used for welding fixtures. Think about those times when you need to hold parts at specific angles and orientations so that you can get a good clean weld. And it's easy to create these customized geometries on a printing system because you're not near as constrained as you are with a traditional machining method. And then we see assembly fixtures. We see this used all the time for electronics assemblies, any assemblies that are mechanical with multiple parts and springs and pins. And so assembly fixtures, that's another great use case for Markforged systems. And then even inspection fixtures. If you think about a CMM machine or a coordinate measuring machine, which is used to verify dimensional accuracy on parts after they're produced, these parts have to be supported. And usually that geometry is unique and sometimes it's complex. And so Markforged parts are a great way to produce these complex fixtures that have unique geometries. And so you can hold the work while you're undergoing inspection. And so fixtures and jigs. So there's all sorts of applications in this realm for Markforged. The other category I want to mention is tooling. And so we're seeing these parts being even used for some sheet metal bending applications. And usually it's the lighter stuff, but this allows you to quickly produce the bending fixture and understand how it's going to perform and even use it to produce your parts. So that's a great quick way to produce these bending fixtures. They're even being used in molds, thermoset molds. And again, that would be a great application for that high strength, high temp fiberglass reinforcement. And then custom tools and clamps that you see around the shop. And in this case, we have a clamp that's pneumatic, and they've designed it so that the parts work well with an extruded aluminum profile. So any of those custom clamps, any of those tools and fixtures are great for Markforged systems. And then I also want to mention in-use parts. And so usually for lower quantities, the Markforged systems can keep up with in-use part design. And the one I want to show you here is this wheelchair steering assembly. And so this was from a company called Eiger. And take a look at the part geometries in this assembly. We're seeing a lot of parts that would be oriented in the XY plane for printing. And so you'd be able to fit a lot of fiber in these types of parts, and they'd be very strong. And so complete assemblies for in-use parts are being produced on these systems. And then enclosures. A lot of times enclosures have thin walls that won't allow you to fit fiber, but there's still applications for them because the onyx by itself has a great cosmetic finish. Especially compared to other machines on the market, the onyx finish is excellent. And so enclosures for prototyping, getting to the right solution quicker by doing multiple revisions. That's all great low-hanging fruit for these Markforged machines. And then we have end effectors. And so that's those gripper jaws. A company called Dixon Valve was able to make huge savings by changing from a machine jaw to a printed jaw. And so think about Kevlar reinforcement in a case like this. And so that could really go into tooling, but it's also being used as an in-use part for Dixon Valve. So that's just a few applications that are out there. And I really want to show this to you just so you can get an idea of some of the spectrum of these systems. And hopefully it will ignite some of your own imagination and help you understand how you could implement this technology into your own workflow. And so with that, that really caps off the content for you guys today. Let's go ahead and take a look at a few questions here. Looks like the guys in the chat have been busy. Oh, it looks like they got quite a few of them answered already. Okay. We had one question about the symmetry of the fiber on a specific layer. And so the fiber can change from layer to layer if you're looking at how it's laid out in a specific area. And then reinforcing with holes, again, that's a great strategy for providing that additional part strength, especially if you're using bolts or compressive forces from bolts. Let's see what else we got here. We had a question about dimensional tolerance. So these systems can generally produce parts around plus or minus 0.005 of an inch. And then that's in the X and the Y plane. And in the Z plane, it's constrained to the layer height itself. And so for the carbon fiber reinforced, it'd be 125 microns, but you could bring that down to 50 microns with an unreinforced part. And we're about out of time now here. So I want to thank you all for joining this session. If you have any additional questions, feel free to keep dropping those in the chat. We'll be on standby here for a little bit. And I also want to encourage you to go check out the Markforged booth because we'll be able to more specifically answer some of your questions and talk to you on a one-on-one basis there. And so again, thanks for tuning in, and I hope you enjoy the rest of the conference. We do have some more exciting sessions for you. And I also encourage you to check out the session tomorrow on additive manufacturing and additive technology and modern manufacturing. We're going to have a great session for you there. And with that, we'll talk to you next time. Thanks.